Here we're going to really test our understanding of electric fields and vectors by calculating the electric field due to 2 point charges at this particular point P right here. So I'm going to do this problem on the light board and stick around because at the end of this light board problem, there will be an additional question for your concept engagement.
Here we're going to find the electric field at a point due to 2 point charges. We've got a charge Q1 of 7 microcoulombs, and it is sitting at the origin of an XY coordinate system. And then we have a charge Q2 that's at a distance of 0.3 meters away from Q1 along the x-axis. And Q2 has a charge of -5 microcoulombs. Find the magnitude and direction of the electric field at point P, which has a coordinate of y is equal to 0.4 meters. So if y is equal to 0.4 meters, the x component is 0, and we're only 0.4 meters above the origin right here along the y-axis. So at point P, we have to evaluate the electric field at this point due to these 2 charges. So I guess that's what we're looking for, E. We're going to get the magnitude and direction of this electric field, so we're going to get all the information about this particular electric field. So we're going to get the full vector. Now the first thing that we're going to do is what I like to do before I start doing any calculations is to think about the directions in which these electric fields are behaving. So the electric field at point P here is going to be, maybe I'll just go ahead and write this equation first actually. The electric field at point P is going to be the sum of the electric field here at point P from Q1 and the electric field at point P from Q2. So we have to add the electric fields from both of these charges at point P together in order to get the total electric field here at point P. All right, and these both have x and y components. So EPx is equal to E1x plus E2x. EPy is equal to E1y plus E2y. Okay, now let's just go ahead and draw in the field vectors at point P from each of these 2 charges. I'm going to do that in a different color. Okay, now remember that our electric field vector always points away from positive charges. So for the electric field at point P from Q1, that electric field right here is going to be pointing upward and away from Q1. So we'll label this as E1. Okay. Now the electric field from Q2 at point P, let's see if I can draw this in here, is going to be directed along this line between point P and Q. Our vectors for electric fields always point away from positive charges and toward negative charges. So the electric field at point P due to charge 2 is going to be pointing in this direction. Okay, so that is my vector for E2. So we're going to add these two together, and then we'll get our total vector, the sum of E1 and E2. That's going to be kind of pointing off somewhere kind of in here, kind of like the average of these 2 vectors together. Okay, now we've drawn in those. Now we can proceed in finding the x and y components of our electric field vectors. I also went ahead and set up a little table to kind of keep track of the quantities that we're going to find. So I have a table here that gives me my vector E1, E2, and EP, and I'm going to put the x and y components for each of those. And that will help us better organize our quantities over here and maybe help us make more sense of where things go together. All right, so let's find the magnitude of my electric field E1. The magnitude of my electric field E1 is going to equal Coulomb constant times the magnitude of Q1 all over R squared. R is this distance between my charge and where I'm finding the electric field. So this is going to be my Coulomb constant, 8.99 times 10 to the 9 Newton meters squared over Coulomb squared times Q1 was 7 microcoulombs, which is times 10 to the minus 6 coulombs. And then we'll divide that by R squared. In this case, the distance between Q1 and our point P is 0.4 meters squared. The magnitude of electric field from charge 1 at point P is then 3.93 times 10 to the 5 Newton over Coulomb. Now, this electric field vector at point P is only in the vertical direction. It has no x component. So this magnitude of my electric field vector, E1, is the full vector for the EY component. There's a full EY component. So there's no x component of E1, and it's all just 3.93 times 10 to the 5 Newton over Coulomb. It's positive, that y component, because our E1 vector is pointing straight up. E1 was the easy vector. Now let's move on to E2. The magnitude of E2 will be Coulomb constant times Q2 over R squared. R is the distance between Q2 and our point P. So this is going to equal 8.99 times 10 to the 9 Newton meters squared over Coulomb squared times Q2. This is, we want the magnitude of this, so we're just going to say 5 microcoulombs, which is 5 times 10 to the minus 6 coulombs. And we have to divide it by this distance between Q2 and P. We haven't found that quantity yet, but it's easy to do. Here we have a right angle triangle. We've got a leg of 0.3 meters, another leg of 0.4 meters. To get this distance here, this is essentially the hypotenuse of our right angle triangle. We'll just use Pythagorean theorem. So this distance, R squared, is equal to x squared plus y squared. So R squared is equal to x squared plus y squared. You take the square root of both sides, so R will be the square root of 0.3 meters squared plus the y component, 0.4 meters squared, and that gives us a distance of 0.5 meters. Okay, this is what we often call a 3, 4, 5 triangle. If you have a right angle triangle, one of the legs is 3, the other leg is 4, then the hypotenuse is going to be a distance of 5. Or here they're multiplied by some factor of 10, so 0.3, 0.4, and 0.5. Over here, my distance will be 0.5 meters squared. The magnitude of E2 is 1.80 times 10 to the 5 Newton Coulomb. Okay, so remember when we drew our E vector here, E2 vector, it has both an x component and a y component. We have to get the x component and the y component of this vector E2. So this is E2x, and this is E2y, okay? So in order to get my components E2x and E2y, I have to know something about this angle theta up here, okay? So that angle theta it's this angle inside this right angle triangle. To find that angle theta, I get to use sine, cosine, or tangent in order to find it. I now know the length of all three of the sides of my triangle here. So let's use tangent to figure out what this angle theta is up here. Maybe I'll do that, I don't know, I'll do it right here. Tangent of theta is equal to my opposite side, 0.3 meters, divided by my adjacent side, 0.4 meters. So theta is the inverse tangent. So we got our meters cancel on top and bottom. 0.3 divided by 0.4. Okay, so this angle theta is 36.9 degrees. All right, well, why did I do that? Well, we need that angle so that we can get the x component and the y component of my vector E2. Well, let's think about the x and y component of our E2 vector. So we can draw another little triangle, which is what I've done right here. You know, it's got its leg of E2x, its other leg of E2y. This is a right angle triangle. And the hypotenuse of that triangle is our magnitude of our vector E2. So we can get this component E2x and this component E2y by using sine or cosine, because now we know the magnitude of E2 already. Well, let's use cosine. Let's say cosine of that angle theta there is equal to my opposite leg of this little triangle right here is E2x, and my hypotenuse is the magnitude of E2. So E2x equals the magnitude of E2 cosine of my angle theta. Now we can do the same thing for the y component of E2. But in this case, the y component of E2 we can get from sine. Sine of my angle theta equals E2y over the magnitude of E2. So E2y equals the magnitude of E2 sine of my angle theta. So this marker is running out here. Sine of my angle theta. Okay, so this angle theta was our 36.9 degrees. And our magnitude of E2, that's what we just calculated right here. That goes there, that goes there. We'll plug those quantities in, and then we'll get that our x component of E2 is equal to 1.08 times 10 to the 5 Newton per Coulomb. And our y component of E2 is 1.44 times 10 to the 5 Newton per Coulomb. But, let's go back and look at our E2 vector. You see that the x component is in the positive x direction. So we've got our, we could just put a, this is positive here for E2x. But our y component of E2 is negative. It is pointing downward. So we actually need to put a minus sign in front of our component for E2y, because that part of the vector is pointing downward in the negative y direction. So now if I fill in my chart with my components, x and y components for E2, I've got 1.08 times 10 to the 5 Newton per Coulomb for the x component, and I have minus 1.44 times 10 to the 5 Newton per Coulomb for the y component. Now what's left is to add up the x and the y components for E1 and E2 in order to get the x and the y components of our electric field right here at point P due to the presence of these two charges. And actually, with the way we have this table set up, we can just add straight down. Because our electric field at point P, the x component is E1x plus E2x. So that's these two components added together. So the x component of EP is just 1.08 times 10 to the 5 Newton per Coulomb. The y component of our electric field at point P is going to be the sum of the y components from E1 and E2. And that's just adding these. We've got minus 3.93 times 10 to the 5 Newton coulombs plus negative 1.44 times 10 to the 5 Newton over Coulomb. And that, we add those together, that gives us an x component for the electric field at point P of 2.49 times 10 to the 5 Newton over Coulomb. Okay, so we're not quite done yet. So this is EPX. This is EPY. And we have to still work with those two quantities in order to get the magnitude of EP and the direction of EP with respect to the positive x-axis. I've erased what we had right here, so we've got a little bit more of a clean slate. Let's go ahead and look back at our diagram and put in our x and y components of EP. So our x component is going to be positive, it's going to be like this. Our y component of EP is also positive and it's going to be pointing up. So then that means that my EP vector, my electric field at point P, due to charge 1 and charge 2, is this vector right here, okay? We've got the x component. This quantity right here is EPX. We've got our y component. This part right here is EPY. All right. So now, and actually there's also this vector in here too, which I'm going to, or angle in here too, which I'm going to call phi, the Greek letter phi for that angle. Now, to get the magnitude of EP, which is the hypotenuse of a triangle with legs EPX and EPY, we'll say that the magnitude of EP is equal to the square root of EPX squared plus EPY squared. So that will equal the square root of my 1.08 times 10 to the 5 Newton per Coulomb squared plus, I've got my 2.49 times 10 to the 5 Newton per Coulomb squared. That gives me a magnitude of 2.71 times 10 to the 5 Newton per Coulomb, okay, for EP. And now we get to get this angle phi. That's our angle that our vector is with respect to the positive x-axis. We've got our angle phi, we've got our legs EPX and EPY. So tangent of phi is equal to opposite side EPY over my adjacent side EPX. So phi is the inverse tangent of EPY over EPX. Okay, and you can plug those in from our table up here, and that gives us an angle of 66.6 degrees. So the full answer for my problem, what is the magnitude and direction of the electric field at point P? That full answer would be 2.71 times 10 to the 5 Newton per Coulomb at an angle of 66.6 degrees from the positive x-axis. That is our vector EP, the electric field at point P from our charges Q1 and Q2.
Now that we spent all of that time thinking about how electric fields can add together in that particular problem to find the net electric field at some point, let's think about this question right here. We have two small charges, positive Q and negative Q, and they're located along the x-axis like here at points that are equidistant from our origin in the middle. Which arrow correctly shows the net electric field direction at point P here on our axis? Now, in order to solve this problem, you have to think about, okay, what's the direction of the electric field from this charge at point P? What's the direction of the electric field from this charge at point P? And how might they add together? And so you've got, well, you've got 5 different choices here that you could make. And I'm going to show you how we could do problems like this, or at least think about problems like this. I'd like for you to think about it conceptually, but we can also use a PHET simulation to help us understand this problem in particular. Let's set up this, this question I'm asking you in the mini lecture. I'm using a PHET simulation about electric charges and electric fields. So here I've put up a grid in the background, kind of help me understand where I'm placing things. And just like my, well, you know what, I'm going to do the opposite of what is going to be in your mini lecture question. I'm going to place a negative charge to the left of someplace I'm going to call the origin, and a positive charge to the right of someplace I'm going to call the origin. And I'm going to evaluate somewhere up here, maybe point P, somewhere directly between but above these two charges. I'm going to evaluate the electric field at that point. So for this configuration, what I can do is I can bring in this little yellow dot here, which is the sensor, put it here, and it's telling me, the sensor is telling me the direction of the electric field at this point. I could click on the full electric field vectors so we can see that. But at this point right here, where I'm evaluating the electric field, the total electric field vector is pointing to the left. Okay, so why does that make sense? Well, remember that our electric field vectors point toward a negative charge and away from a positive charge. So at this point right here, I've got my electric field from my positive charge that's moving off in this direction. At this, because of my negative charge here, the electric field wants to point toward my negative charge. And so the electric field at this point from my negative charge is going to be pointing toward it. So we've got this electric field for my positive charge, this electric field for my negative charge, and the sum of them together are going to add to give me a net electric field just along the negative x-axis. Okay, these both have the same magnitude of charge. Now this size of this vector can change, and the angle of this vector can change from the positive x-axis and negative x-axis here, depending on the size of the charges here. But since we both of these charges are of the same magnitude, then this problem becomes a little bit more tractable for us. So you could use the simulation, or you could just think about the problems. What happens when I swap my charges? So they have a positive charge on the left of the origin and a negative charge on the right of the origin. What will be my electric field vector at some point along the y-axis directly between the two?